How are you, everybody who is watching this video? I'm very happy to have you today. I would like to take this opportunity to welcome some physical students who we are going to learn together the most called digital electronics. And also I would like to welcome the online students who are not a part of this physical class. My name is Olenjolai. If it's the first time to meet me, I'm very happy to have you. And today I have a good news concerning about digital electronics. This is the very important branch of electronics engineering. But the goodness of the digital electronics, we can teach students who are specialized in electronics, or in electrical, or in computer engineering, or in mechatronics. But also you can teach these modules to other related fields such as mechanical. For instance, in this physical class, I have some mechanical students who are pursuing bachelor in mechanical engineering. Those are the students that I have. I will teach these contents in relation to what they are covering or they are learning usual in aspects of mechanical. But the language that we are going to speak is about digital electronics. These contents, because this is actual fundamental, we are introducing them digital electronics for the first time, and actually are transforming them from the digital electronic science that they have been covering in A-level educations or in ordinary diploma education. So this course is very interactive. We are going to have theory in this course. We are going to have simulation. We are going to have practical. So you have three parts. For today, we'll be focusing on the theory of the digital electronics circuits. So if that's the case, what is required for lecture 1, so just for workshop 1, just a fresh mind, have your exercise book, have your pen, have your pencil, because we are going to draw. And if you want to sound as engineer, you have to like drawings, and especially by using the pencils and rubbers in order to clear or to clean your drawings. Even if your drawings on the exercise book, but we prefer students to learn and have a traditions of drawing by using the pencils. So if you have those requirements and you have a fresh mind, let us go into today's class. But before I take you into the lecture 1, let me acknowledge the presence of some physical students who are handsome boys or handsome gentlemen and beautiful girls. How are you, students? How are you, engineering students? Are you fine? How about your neighbor? Is he fine or she fine? Okay, greet your neighbor before you start the class. Tell him or her hi or hello or how are you? Do you like mechanical engineering? Why are you studying mechanical engineering? Yes, so if you ask that question, then say, okay, I will answer you later on. So let us continue with the digital electronics. And we are in chapter 1 that called the combinational logic circuits. Then this is lecture 1 that called the digital circuits. Let me do the quick review of what we've covered in lecture 00. Quick review. Say quick review. So quick review is actual a brief or a connection between lecture 1 and lecture 00. So in lecture 1 or in lecture 0, what I have taught you, firstly, I taught you how we can define in the simple language the terminology that we call the engineering. What is engineering? Because we are learning mechanical engineering, we are learning electronics engineering, we are learning electrical engineering, but what is engineering? Then simply I told you that there's a different ways that you can define this word engineering, but the simplest one, engineering simply is the purposeful use of what? Use of science. So engineering is the purposeful use of science. Before you learn engineering, you have to be or you have to learn about science. And the good thing that in our educational system that Tanzania, we learn science since standard 3 up to NTA level 6 or up to Form 6. So we learned science for almost 11 years. 11 years, some of the students in this class, you've been learning science possibly for almost 9 years. Then, the next terminology, because I was teaching you about the terminology, we defined what the meanings of the word electronics engineering. So we said electronics engineering simply, this is the purposeful use of what? Electronics what? Electronics science. Electronic science we have been introduced in primary, but very little, but in all have been introduced less. Concerned about semiconductor, transistors, diodes, and that's all. But in the A level, we have been introduced by having 5 subtopics of electronic science. And one of the subtopics, which is actual that, I think that the first one is called the digital electronics. All right? Then we defined, we said, okay, because in this class, we have mechanical engineers. What is mechanical engineer? Or what is mechanical engineering? Then we came up with the definition that mechanical engineering is a purposeful use of what? Mechanical science. So before you have a vision to be a mechanical engineer, you should go through the mechanical science. And the good thing that for A-level education, we had almost 13 topics. 14 topics that we are preparing us, or we are training us about mechanical engineering. In mechanical, or in mechanics, we had 11 topics, but another topic which is very important in mechanical engineering is called the heat. So where we had 3 topics, thermometry and thermometers, heat transfer, and thermodynamics. And the good thing that nowadays you have a module called the first is thermodynamics law, second thermodynamics law, third is thermodynamics law. But that is in engineering aspects. Are we together, students? Then we discussed with you after defining mechanical engineering, electronics engineering, and whatever. Then we discussed some other issues. But again, I say let us get the answer. Why do we teach? Why do we teach mechanical engineering students digital electronics? Why do we teach you this module? Why should we teach you about digital electronics? Why should we teach you? Very important question. I gave you at least 3 reasons. The first one, I told you that digital electronics, actually, it's the heart of the most modern mechanical system. Right? So if you say heart, actually we refer about our own hearts as the human heart. So our human hearts actually perform different functions. If our hearts fail to perform a particular function, then we don't have life. So in case that you hate digital electronics because it's not a mechanical module, then we want to tell you that you'll be dealing with classical mechanical system. You won't deal with modern mechanical system. Right? The second reason I told you that most of this it means that digital electronics consists the control or the brains. It's the one that makes the brains of most modern mechanical system. That's another reason. So if you want to say that, okay, this is the modern mechanical system, there's no way that you can define that this is the modern mechanical system without the presence of digital electronics. And I gave you a simple example for a mechanical, called a mechanical motor vehicles, which actually that we have them. And they consist, we say that mechanical because the large part is the mechanical. For instance, we have cars which have manual gears, and we have cars which is automatic gears, right? Yes. So when you say about manual gears, you know that it's a challenge. If you want to experience how manual gears brings a lot of challenges, just take a dala, and then find the place that where the conductor has to make a corner. Then you'll find that just is actually actually is what changing gears. And then for automatic, what you have to do? Actually that you have to just see, it's simple. You just press, and then everything is accelerating or decelerating. So the automatic cars, we call them the mechanical vehicles because the large part is mechanical. So what makes the automatic gear? It's actual digital electronics. Are we together? Are we together, class? Yeah. Then I told you about engineering language. This is very important. I have to remind you because today we are going to enjoy it in detail. Engineering language. So we say that in engineering we present our ideas or solutions for the particular problems by using 5 phenomena. The first one, engineering is all about numbers. Engineering is all about numbers. If you cannot communicate the engineering's information, whether mechanical engineer without numbers, then actually call to your political mechanical engineer. Right? Then engineering is all about a formula. So if you want to communicate, for instance, if you want to communicate a message in engineering and you can write 1 page, it's better even that page to write just by using formula. Just use the formulas and communicate because that's the simplest language. Every technical engineer will understand your message. So formula and equation. And this is the applications of applications of mathematics in engineering. Are we together? Yes. Then practical engineering language has to be presented in terms of diagrams and the drawings. Why did I add the word drawings? Because you are the mechanical guys. You have to draw a bush. You have to draw a bolt. You have to draw a nut. And I think that actually that you have to be competent in drawing mechanical more than even some other fields. You have to draw in AutoCAD. Okay? So the practical engineering language is all about diagrams and drawings. Say diagrams and drawings. Again, say diagrams and drawings. Then we say that we can present the engineering message, a special practical one, by using tables. Say tables. Tables. Say tables. We call them table 40 results. And in this module, I will show you how do we get numbers, how do we get formulas, how do we get the diagrams and the diagrams, how do we get tables. That's my responsibility as your teacher in this module. Right? And then finally, I told you that the engineering method or the engineering, the practical engineering language is all about graphs. We have to love graphs. And I told you that ask your neighbor, how many graphs have you drawn since you began your journey of learning mechanical engineering? So your neighbor for that day then actually lied it to you. Some of them said 2 or 3, right? Then I told you, tell your neighbor in lecture 1, in the next lecture, to come with their graphs. So possibly your neighbor today has some graphs. So take just a few seconds to ask your neighbors about the graphs that he or she has drawn since semester 1. It's time for you to communicate to your neighbor. So what did you get? Did you see one? Can you see one of the graph? No, it's not there. Okay, so that is the quick review of what we've discussed. Let us continue today with digital circuits, digital electronic circuit. So the subtitle of today is digital electronics circuits. So let us carry on. Class A, digital electronic circuits. Again, class A loudly, digital electronic circuit. Digital electronic circuit. The fundamental question, what is digital electronic circuit? What does it mean? What is digital electronic circuit? So here we have a fundamental question. What is digital electronics circuit? So digital electronic circuit, we say that simply the digital electronic circuit, a digital electronic circuit is the type of electronics circuit which contains or consists different digital electronics components. Which consists of different digital electronics components that process digital signal. So a digital electronic circuit, class A digital electronic circuit, say it happily, say digital electronic circuit. Yes, it's just like how you support Yanga Sport Club or Simba or Manchester. You used to support them with gladness, and nobody is telling you that you celebrate. You just celebrate yourself from the bottom of your heart. Today I'm happy. So digital electronic circuit, this is the one of the type. In electronics you have so many, or we have different types of electronic circuit, which consists of different digital electronics components. In electronics we have digital electronics components, we have analog electronics components, we have also power electronics components. Okay? And also we have digital electronics instruments, we have analog electronics instruments, and also you have power electronics instruments. So this one, or these circuits, consist of digital electronics components, but what the function of these digital electronics components? To process digital signals. Say digital electronics components. Say loudly, digital electronics components. They then say digital signals. Yeah. So remember that we can have, so stop writing. A digital circuit might consist or might be a pure digital circuit, or might be a partially pure digital circuit. Listen, I won't write this one, I'm just explaining. A digital circuit might be pure digital circuit, or might be partially pure digital circuit. Hello, 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 hello there. Hello. How are you? Are you okay? What's going on there? Okay. You are far from here, eh? Wonderful. Then, a pure digital circuit, this is the circuit which consists only digital electronics components. Are we together? A partial pure digital circuits, these are the electronic circuits which consist mainly digital electronics components, and some of them might be analog electronics components or power electronics components. Can I repeat? Okay. A pure digital circuit, it's a circuit which consists mainly digital electronics components. You can take a note, you can write down. Digital electronics components. Only digital electronics component. A partial pure digital electronic circuits consists mainly digital electronics components and also some other electronics components such as analog or power electronics components. Let me repeat again for the partial pure, right? Yes, my students there say, oh, sir, repeat again. Partial pure digital electronic circuits is a circuit which consists mainly digital electronics components. Right? Mainly. When I say mainly, I mean that the large part is digital electronics components. But also it consists might consist some other analog electronics components or power electronics components. Is it clear? Is it clear? Yeah, very important. Then we have another vocabulary. When we've been defining the terminology called the digital electronic circuit, we found another vocabulary. And what the names of that vocabulary? Digital signal. Say digital signal. Say digital signal. We have to understand what does digital signal mean before we continue. Because these digital electronics components process digital signal. So what do they process? We have to understand them first. Because in this course, we are going to deal both. We're going to deal with digital electronics components and digital signals. Are we together? Are we together, class? Yeah, so this is the first terminology. The second terminology, digital signals. Digital signals or digital signal. Say digital signal. Again, say digital signal. Ask your neighbor, my neighbor, are you going to dream tonight about digital signal? What the response? What's your neighbor's response? Yes. I think that to dream about digital signal is better rather than to dream that you've been chased by a snake. So digital signal, this is a type of information, is the types of information. This is the type of information signal. This is the types of information signal. Types of information signal. This is the type of information signal that or which has only two states. So a digital signal, this is the type of information signal. Say information signal. Say information signal. Which has only two states. That's the meaning of the digital signal. So analog signal has more than two states. Digital signal has only two states. Remember that in electronics engineering, we have two types of, mainly, we have two forms of the signal. We can have, or we have a signal we call the information signal or data signal. And we have also the signal we call the power signal. Stop writing, please. Listen. In electronics, especially whether in digital electronics or analog electronics, we have two types of we have mainly two types or two categories of signals. The first one, we can have power signal. Say power signal. Say power signal. We always get a power signal from the power supply. Are we together? Which for the mechanical aspects, the power signal, we get it from the source of energy. Whether it's a diesel, whether it's kerosene, whether it's a gas, whether it's petrol. So because it's the one that providing the energy for that vehicles to move, or maybe for the for something, for some mechanical system to work, then we say that what it will be received from the power source, we call it the power signal. Are we together? Then we have another categories of signal, which we call it information, or sometimes we call it data signal. Information or data what? So information or data signal, what does it mean? For instance, we say that we get a power signal from the fuel. From the fuel or from the let's say that from what? We get the information, the power signal from the kerosene or from the petrol or from the diesel, right? But remember that when, for instance, you are changing a gear, also you are sending what? A signal, a mechanical signal, right? So when you change a gear, actually that information will be sent to the brain of the motor vehicle, which is engine. Are we together? So that signal will be interpreted by the engine that this is information signal. Why is information signal? Because it's carrying a particular message rather than power. That now change the gear from first number 1 to gear number 2. Are we together? Are we together? So in case of the gearbox, we have gear number 1, number 2, number 3, number 4, number 5, for instance. All of them, they have a definition that those we call them information or data signal. Similar in electronics, for instance, in your keypad, you have number 1, number 2, number 3, number 4, right? When you press number 2, that's the information signal, which will be received by the processor. And know that, okay, now let me display number 2 on the display. Are we together? Are we together? Yeah. So digital signal, this is the one of the types of the information or data signal, which is only 2 states. And what are those states? Those states in electronics we have, we can present this system, the two states of digital signal may be presented in 3 formats. 3 formats. The first one, this can be presented as high, and the other state, the second state, as low. The first state is high, the second state can be presented as low. Then, we can present that digital signal in this state that can present as bit number 1 or bit number 0. Okay? Okay? Hello? What's going on with your neighbor? So you can present as high or low. Say high or low. High. 1 or 0. So 0 has a very important meaning in digital electronics more than you think. Usually, in terms of marks, if you score 0, you're a failure and you know nothing. But in digital, if you have 0, you have something. And very important. Okay. Then also this digital signal, we may present as a 5 volt or we may present as 0 volt. 5 volt or 0 volt. In terms of Boolean algebra, we present these digital signals as 1 and 0. In terms of real or practical electronics, we represent the 1 or 0 in terms of voltage. 5 volt or 0 volt. Say 5 volt or 0 volt. Yes, sometimes you can find in some of the books we say that this 5 volt can be broken down. It can be 4.5 volt up to 5.5 volt. Or, not all, this is actual ND, and this is ND, because these are the 2 states. ND. For the 0 volts, you can find that we say it's 0 up to 1 volt. So, if you examine, we say that, simply say that, this is not before. Digital signals are the levels, are the two levels of voltage. So these are the 2 levels of 40 of voltage. So you have a high level and also you have a low level. Again, let me just keep open your mind. We used to have, stop writing. We used to have bit number 1. Okay? This bit number 1, we may represent by 5 volt or we may represent by 0 volt. This now you have to be careful. We are speaking the engineering language now. We are no longer speaking the science language. I said stop writing, look on the blackboard. In mathematics or in Boolean algebra, we know that we used to deal with bit number 1. Bit number 1. So bit number 1 may be presented by 5 volt or may be presented by 0 volt, depending on the situation. Also, bit number 0 may be presented by 0 volt or may be presented by 5 volt. So you should not claim that bit number 1 is always presented by 5 volt. It might be 5 volt or 0 volt. Right? It depends. Then you should not claim that because the bit number 0 is presented by 0 volt. No. It can be presented by 0 volt or 5 volt. For instance, some of the digital sensors, if there is no any signal which has been sensed, it provides 5 volt. When that digital sensor senses a particular signal from the source of the signal, then it's providing 0 volt. Class, are we together? Yes, because 0 bits is actually 0 related with 0 volt, yeah? And 1 is, 1, 1, 1. We used to claim 1, 1 is 5 volt. No. That's not true. If you have any question about digital signal, please ask it now. Class, if you have any question about digital signal, please ask it now. I told you, be serious with this stuff because you need them in your field. You have any question? Okay, no. Then another piece of information is important information before we focus on the digital circuits, because today the subject is actually about digital electronic circuits. It's about the waveform. We call them waveforms or timing. Some we call it timing diagram of digital signal. So we have only 2 digital signal, which is high and low, or 1, which is high and low, or 1 and 0, or what? 5 volt and 0 volt. So the timing diagrams is actual waveform. When you say about timing diagrams, we mean about waveform. Say waveform. Say waveform. Yes. Waveform is all about graphs, which is all about engineering language. So the waveform, we say that, look, the timing diagram, stop writing. And you have drawn them by using the pencil. For instance, if you have this timing diagram, like this, and then here we have this guy, and then here we have this, and then here we have this, and then here we have this, and then here we have a 4. This one, then we say that, okay, so let us having that this is one state, and this is another state, and here we have another state, here you 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 have another boundary. I say this, stop drawing, stop writing, look and listen. Please check your neighbor if he or she is watching on the blackboard. So for this one, this is 0 volt and this is 5 volt. So remember for the analog signal, we say that it's continuous. So it's changed, it is continuously changed. It has different states, right? For the digital signal, it has only 2 states, either low or high, full stop. So for instance, this is 0 volt from here to here. So this is 0 bits, 0 volt, and also here we have 0 volt. But once we reach at this point, then the signal rise up. Rise up, we call it with a straight line. It does not actually that going and having different values, no. Are you together? Then, between this one and this is BT1. And then, between this one and this timing, this is BT1. And also this is BT1. And here we have 0. And here we have 0. And here we have 0. Here you have 1. Here you have 0. We have 0, 1. So that is the timing diagrams that we have in digital electronics. Right? So we presented the digital signals either by using the time diagram, we may present them by using the truth tables, we may present them by using the Boolean algebra. I told you that engineering is all about what? Graphs. Engineering is all about what? Graphs. So that's why that we have a digital graph. So these are the digital graphs. They have only 2 states. Class, are we together? Yeah. Yes? You have a question? You said yes, I. Okay, good. Then, once you know the meanings of what the meanings of digital electronics circuit, and also you know what the meanings of digital signals, now let me take you into the types of digital electronic circuit. We have 2 types of digital electronics circuits, and then today we'll dive into the first one. Types of digital electronics circuits. Types of digital electronics circuits. Types of digital electronics circuits. So, in electronics engineering, there are only 2 main types of digital electronics circuits. Namely, the first one, we call it combinational logic circuit, and the second one we call it sequential logic circuits. Say combinational logic circuit. Again, say combinational logic circuit. And then the second one is equal to say sequential logic circuit. Say sequential logic circuit. So ask your neighbor, what the meanings of combinational logic circuit? Does it combine? And what the meanings of the sequential logic circuits? Does it do some sequences? Does it need the knowledge of sequence and series? So, ladies and gentlemen, let us discuss about the first type. Combinational logic circuits. Combinational logic circuit. And the fundamental question that we have, this will be question number 3. What is combinational logic circuit? Class A, combinational logic circuit again. In mechanical engineering, we use combinational logic circuit and also use sequential logical circuits. How do we use sequential logical circuits? Because in mechanical system, sometimes also we need to get the history. We need to get what? The history. For instance, if you are driving a car from Dar es Salaam to Morogoro, you can have the records of the stops along the way, along the road. So I mean that the function All those stops have been recorded by a memory element. Okay? Yeah. So combinational logic circuit, we say that so a combinational logic circuit is the type of digital electronics circuit. The type of digital electronic circuits in which its output at any time depends only on the present combination of the inputs with total disregards of the past state. Of the inputs. This is the simple definition of combinational logic circuit. There are different ways that you can define combinational logic circuits, but one of them is that way of defining by using those keywords. Stop writing. Let me explain this definition, then we move on. Class A combinational logic circuit. Speak it loudly. You hear, for instance, that the amplifiers, those are the instruments actually that they are providing much sound rather than you. Say combinational logic circuit. Your volume is still low more than the speakers, which are non-living things. Okay, so a combinational logic circuit, this is the type of the digital electronic circuit in which its output, say output, at any time, say at any time, depends only on the present combination of the inputs with total disregards of the past state of the inputs. Simply, listen, if you want to understand combinational logic circuit, you have just to remember about one type of the tense. Do you know that we have different types of tense? Mainly we have three. Past tense, present tense, and future tense. Where? Okay, so we have past tense, present tense, and future tense. One of our classmates here, one of our colleagues, was real doing something inevitable in this class. So we have to make sure that we apply the external force. Everybody continuing to state of rest or motion unless there is an external force Yes, first Newton. So what actually I have done, I supplied what external force to somebody in our class. And that external force has actually made you to be happy. Okay, so we say that this is the type of the digital electronic circuits in which its output at any time depends only, say only, on the present combinations of the inputs with total disregards of the past state. Simply, I just want to explain to you and clarify the definitions of combinational logic circuit by just using the tenses, the two types of tenses, or three types of tenses. We said we have past, present, and future tense. Past is actually tell us about the events which have already taken place. Present is actually telling us what we are doing right now, or what is taking place at this time. Future is actually telling us about what will be the future, or in next time. So simply, these combinational logic circuits, we can just see, learn them or understand them as how we understand present tense. Present tense. For instance, now I say, I am teaching, or I teach. So the output of these combinational logic circuits depends only the combinations of the inputs. It does not depend any past states of the inputs. What does it mean? For instance, if now this is input 1, this is input A, and this is input B. Okay? Then we say that I have an output. I have an output. Hello? Hello, hello? What's going on there? I'm still in class. This is input A, input B. These are the inputs. We have two inputs, right? And this is the output. Are we together? So this output depends on how we combine input A and input B today and at this time. It does not depend if we combined input A and input B yesterday. That's the meanings of this definition. Simply depends on the present combinations, or depends on the present combinations of the inputs. How you combine these inputs at this time. While sequential will be opposite of that. Will be depending on the combinations of the present state of the inputs, but also with the previous state. Are we together, class? Are we together, class? Yeah. So let me give you some examples of combinational logic circuits. Examples of combinational logic circuits. The first one, the simplest one, we call it half adder. Say half adder. Say half adder. The second one, we call it, we have a combinational logic circuit, we call it full adder. Say full adder. These are the ones that we use to do addition, subtraction, multiplication, division in scientific calculators. Those two types of circuits. Full adder, we use it oftenly in design calculators. The third example of full adder, the third example of 40 of combinational logic circuits, also in electronics we have some circuits, we call them BCD adders. BCD, this is half adders, full adders. BCD adders. Say BCD adders. Say BCD adders. The first example of combinational logic circuit, we call it encoder. Say encoder. Say encoder. The fifth example of combinational circuits, we call it decoder. Say decoder. At home we used to have decoders, Azam decoders or Zuku decoder. At your home, you have all of them, eh? Zuku, Adam, and what? Star Times, okay. So decoder. So it means that the decoder you are using in your television receiver is a good example of combination logic circuit. So when you go back today, you say, we learned about combination logic circuit, and simple example is this one. The sixth example of combination logic circuit is called the multiplexer. Say the multiplexers. Say the multiplexers. Then there are the seventh example of 40 of combination logic circuits is called the multiplexers. Say multiplexers. So multiplexers actually this combines different inputs and give one. For instance, if I make separating, multiplexer is often used in communication. For example, in television communication, in radio communication, in cellular communication, even in internet. What is function? Multiplexer is actually receive different inputs and combine them, then give a single input, single output. While the multiplexer is vice versa of this one. Receive a single input which is actually contains different outputs and give different outputs. Okay? So we are using them in television transmission. We are using them in television reception point, and also we are using them in cellular communication. Then the eighth example, because eighth example, we have half subtractor. Say half subtractors. And also we have full subtractors. I know that in your A-level or diploma, you have never heard about this. This is the first time. Say full subtractors. Number 10 is called the magnitude comparators. Magnitude comparators. Say magnitude comparators. So these are the 10 examples of combinational logic circuits that we have in digital electronics. Okay, do you have any question? No. Then, the next part, very important, general block diagram. General block diagram of combinational logic circuits. General block diagram. We say that we presented the engineering information in terms of diagrams, in terms of numbers, in terms of graphs, in terms of formula, in terms of tables. So the general block diagrams of combinational logic circuits separating is simple. There's no need for you to claim it. It's very simple. Here we have power, supply, unit. Here we have control, unit. So for this side, this we call it combinational logic circuit. Then here we have another block. Say the stop writing and stop drawing. Look on the blackboard first. This is input unit. Then here we have an arrow. We have power supplied here. And also the inputs needs also some power. Then the next block is called the output unit. So also we can have one input or more than one input, and here we can have one output or more than one output. So this is figure 1, the general block diagram of combinational logic circuit. Huh? Pardon? Yes, may need the power supply. You can take photos and you write later. So this is the general block diagrams of combinational logic circuits. So this is very important diagrams because it will give you the idea, the overview of what we are going to discuss. We'll be discussing about logic gates later on. So we'll be discussing about some other logic circuits, but simply all the information that we are going to discuss later on based on this block diagram in case of the combinational logic circuits. Stop writing and stop drawing. Listen. How many blocks do you have there? How many blocks? 4 blocks. The first block is called what? Power supply unit. Say power supply unit. It's just like a car. Can a car move without a fuel or gas? Similarly, for us in electronics, an electronic system cannot work without electricity. An electronic system cannot work without what? Electricity, right? So this is the power source. It's just like you. Can you live in this world for almost 2 months without eating anything? Eating or drinking anything? Can you? When did you try? For you, actual 2 days are enough. We might find you in emergency sections at Muhimbili Hospital. So we as a human being, our maximum capacity of living on this planet Earth without taking in any food and without taking in any drink is just 40 days. 40 days. Once you reach or you go to 41 or 42 or 43, you are going to die. That's biologically and spiritually proved. That's why that Moses fasted for 40 days and nights. That's the maximum capacity of the human being. But I and you, even one day, it's what? It's a problem. Once you fast one day, I think that your kitchen will know who you are. because in the evening you prepare breakfast and lunch and dinner simultaneously. Why? Because you have to pay the debt. Okay, so this is actual providing, it's just like the energy, just like the food that you are taking in. So this is supplying power to this input unit, and this is combinational logic circuits, and this is output unit. So listen student. With the power supply, we have 3 types of power supply in electronics. We have DC power supply, we have linear power supply, we have switched mode power supply. Also, in case of the power supply, in most cases it is DC because we need DC in our power system. When you talk about input unit, say input unit. For this case, it can be any part that can give a digital signal. Because these combinational logic circuits need the input from another source. In most cases, for the mechanical or mechatronic system, the input unit is actually used to be a sensor, a digital sensor, with sensing a particular parameter. It might be a pressure sensor to sense what? Pressure of the gas within the tank. And hence provide what? Electrical energy. That electrical energy will be fed at the input of the combinational logic circuit. Then what will be the function of combinational logic circuits? To make decisions that have been given high and have been given low. Have been given maybe in another source that high, high, low. So if I combine them, what should be an output? Are we together? For instance, you know that if in the combinational logic circuits we have the AND gate, actually we know that if you have the high signal from one sensor and a high signal from another sensor, the output will be high. Are we together? If you have high signal from one sensor and low signal from another sensor, the output will be low. Are we together? Then that output usual in science, we use just to draw that this is bit number 1, bit number 2. But practically in electronics or mechatronics engineering, the output unit also might be a load. So a load or another system which need to be controlled by the low power system. So the output unit might be either a sensor, might be either a gas pump, or a water pump, or oil pump, or maybe any hydraulic system, right? Or maybe it can be just like maybe another mechanical system. So sometimes it might be maybe just a gearbox or something whatever that is actually is going to control. Are we together? So when you say about input units, this is the general language. And this is the general, that's what we call general block diagram. So you see that the output will depend the combinations of what? Of the input at this time. There is no any memory element. When I will teach about sequential logic circuits, you will understand the difference between them. Because for the sequential, then the input, one of the inputs or the combination of the inputs will also depend the previous state. How was the previous state? And then so combine with the present state and you get the output. Class, are we together? Yes. Is it clear? Yes. Yeah. So think about the input unit is something that interacts with the real world environment. Think about the output unit is something, it can be either another electronic system or mechanical system or oil and gas system or computer system. So it can be something else which is actual operating with high power or low power. Let me give you a simple example. For example, we know elevators. Do you know electric lift? If you want to request it, maybe you are in second floor and the lift is in ground floor, what do? You just press what? You press a button, right? You press a button. Isn't it? And do you use a lot of energy? No, simple. You just press, then it responds. So when you press, you are providing the input to the combinational logic circuit. Right? And as once the controller receives that, have been requested in second floor, the information will be sent to the controller, and the controller will send to the motors. Because that electric lift is being driven by motors. And those motors always are located on top of the building. Are we together? So electric motors, they either rotate clockwise or anti-clockwise. And remember that those are the three-phase electric motors. So just hit a single button, just a single click, because if you don't click, that is logic state high. If you click, logic state low. Right? Then the PLC receives the signal and send the information to the AC motor. So that AC motor will move the car from the ground floor to the second floor. Once it reaches there, the door opens. So when the door opens, what happens actually is when the information is being sent, then the door opens for people to get within OT or inside the OT, the elevator. So once you are there, then after a short time, because it's been programmed, the door closes. And then the car responds, or actually the elevator moves up or down. Are we together? Yes. So don't think that combinational logic circuits is just for the low power itself. No. This is actual low power, but it can control high power. It can control even three-phase motors and three-phase water pumps, three-phase system. If I say three-phase, I think that you understand as mechanical guys, right? Tunasema kwamba in Swahili we call it elimu uhandisi wa mitambo. Do you have mitambo? Do you have mitambo in DIT? Good. So that is all about the introductions about the combinational logic circuits. Do you have any question? Is it clear? Yeah. The second example, the second types of logical circuits is called what? Sequential. Say sequential. Say sequential. You have volume now. Say sequential logic circuit. Yeah, thank you very much. And this is the question number 4. Ask your neighbor, if you have understood combinational logic circuit, what is sequential logic circuit? Does your neighbor has an idea about sequential logic circuit? She said, she has an idea. So can you give your neighbor a chance to tell us her idea? So none of them want to try. Say sequential logic circuit. The goodness, if you have understood combinational logic circuits, to understand sequential is very simple because you add some keywords. Oh, I think before, not this one, right here, not here. Write this note, the first one. The logic gates that we've introduced you in the A level, the logic, say logic gates. So the logic gates are the most building blocks of combinational logic circuits. So logic gates. So these combinational logic circuits, mostly we manufacture them by using logic gates. Right? Right? Yeah. So a sequential logic circuit, we say that is a type of logic circuits in which its output at any time depends on the present combination of combinations of the inputs and previous or past states of input. So a sequential logic circuit, it's a universal. It means that in combinational logic circuit, it's a subset of the sequential logic circuit. When I say subset, you remember the topic of set. You remember? So if you say set A is a subset of set B, it means all the elements of set A are found in set B. So for the case of the combinational, everything we find in combinational, we can find in a sequential circuit. But some elements of sequential, we cannot find them in combinational. That's the meaning. That's the simple mathematical language, isn't it? Is it clear for you? Yeah. So if you have combinational, simply combinational, it is what? We say that, or sequential, it's a combination of combinational and another part. So a sequential logic circuit, this is the type of logic circuits in which its output, it's what? Output at any time depends on the present combinations of the inputs and the previous or past states of inputs. Are we together? Yes, sir. Yeah. So for the combination, depends only on the present combinations of the inputs, with regards or without dependence on the previous or past state. For the sequential, depend both present combinations of the inputs and what? Previous or past states of the inputs. So when you hear that there's a system which depends on the previous or past state of the inputs, it means that this system must have a memory. For instance, yourself, you remember what you have eaten. Ask your neighbor, what did you eat last night? What did you eat last night? So the information, the answer is there, right? You may not mention, because possibly you have eaten bites, right? Oh, maybe you had a binary number. Say binary number. Yeah. 1, 0. So maybe you had a binary number 1, 0, 0. Or you had a binary number 1, 1, 0. This is breakfast, lunch, dinner. This is breakfast, lunch, dinner. It's very difficult for our country to have a binary number of 40. So you see, digital electricity is everywhere. Even in taking what? Food. Sometimes in Bongoland, you may have a binary number 40. It doesn't mean that you have fasted, but the situation is, it's not 40. Yeah, it's not. It's So digital electronics is everywhere. Is everywhere? So in case that your neighbor asks you, will you offer me lunch today? Then tell him or her, you know that I'm applying binary number. So today my binary number is 101. So just go and take lunch yourself. This is simple. If you teach digital electronics with a real life situation, digital electronics is well understood, right? But life is good because externally we won't see you that if you have a binary number 000. That is internal. Okay, so then we say that, so simply a sequential logic circuit is SOT. So you say that a sequential logic circuit, simply this is combinational logic circuit. So your neighbor remember that what he or she has taken last night. Isn't? Why? Because your neighbor has a memory. If you don't have a memory, you can't remember. So if your neighbor told you that, I don't remember what I've eaten yesterday, you know that there's a problem in memory element. There's a problem in what? Memory. And then you have to be careful with your neighbor because you know already his or her memory has some what? Problems. Okay. So sequential logic circuits is actual combination logic circuit plus what? Memory element. Are we together? Yeah. So this is simple way of keeping the informations about sequential logic circuits. Let me give you some examples. Examples of sequential logic circuits. So the first example is called the flip-flop. Say flip-flop. Say flip-flop. For some of the students who are older enough, we do remember that previously we didn't have a flash, we didn't have CD or DVDs, we didn't have hard disk, external hard disk, we didn't have memory cards, we have something we call it a flop disk. Say flop disk. Because we have a digital age, young guys who are modern guys. So let us tell you about what where are we from in case of variety of the memory elements. So those floppy disk consist of different flip-flop. And in electronics, we have only 4 flip-flops, right? The first one, we have SR flip-flop. Say SR flip-flop. Also, we have D flip-flop. Say D flip-flop. This is one of the topics in this module. Then we have T flip-flop. Say T flip-flop. And then we have JK flip-flop. Say JK flip-flop. For those who have been playing cards, we have a very special card. So some cards, we call them Jokeri. Do you remember Jokeri? So we have 4 types of flip-flops. So flip-flops, this is the example of sequential logic QWERTY circuits. The second example of sequential logic circuits, we call them counters. Say counters. Say counters. Have you ever gone to City Mall and buy some items? Ask your neighbor, have you ever visited City Mall and buy some items? Then when you went to the counter, the counter, you find just a service provider of City Mall, but also there are some machines, and there is something we call a conveyor belt. Have you seen conveyor belt there? Yeah, so actually you place your cup or your basket with items, then they'll be scanned. After being scanned, they'll be counted, you'll be given a prize. So actually there, because the service provider cannot count them manual, right? That's all about applications of 40 counters. But also in traffic light, say traffic light. Yeah. For we who used to drive or take dala. In Bongo, how do we call it? Dala, right? Yeah. Or Haisi or Coast or whatever. For those long dala, how do we call them? Gongolamboto, Kariako, Hitcha. And you understand. Do you used to get in through the window? Yeah. It's your tradition, eh? Yeah. Even now, that's your plan. Okay, so in case of the traffic lights, most of the traffic lights junction, you find that when the red light is on, there is a counter, down counter, right? Actual counting the seconds. Then after that, then the color, actual, it means that maybe the red color is is on. Then you find that the counter starts counting from 60, right? When it reaches 0, then we have a green color, maybe for 60 seconds. So that is actually providing the equality between different parts of the junction. Are we together? So those are the digital counters that we have. Then the third example, we have something called registers. Say registers. Say registers. For instance, nowadays, ask your neighbor, how many contacts, mobile contacts do you have in our mobile phone? How many? 1,000? How many mobile contacts do you have in approximately? 800? 800. Some of them 800. Others 1,000. Others 5,000. 100K. So, do you know any of the number? Do you have any number? Ask your neighbor. Do you remember any number among the numbers that you have in our? Do you remember even 10 numbers among the numbers that you have in a mobile phone? Yes. 10 numbers. Yes. First number, second number, third number. I think that you see your neighbors, how they are watching upon you. That you have a very good memory capacity, isn't it? She has a very good memory capacity. Okay, but if you can remember 10, but you cannot remember 100 numbers, different numbers. right? So it means that the SIM card, say SIM card, it has a register to store the contacts that you are saving. And that's why that whenever you save a number, you may be asked that where do you want to save? Within the memory of the mobile phone or within the SIM card? Oh. Are we together? Okay. So those are the common 3 examples that we'll be discussing. We have asynchronous, we have also synchronous. I think that these are the simple examples as mechanical guys. Then let us discuss about general block diagram. General block diagrams of what? Of sequential. Huh? Where? Wait. I want to talk with you after this class. Sequential circuit. Wait. I'm about to finish. Wait. Okay. So the general block diagrams of sequential circuits. Say sequential circuit. Yeah, so its block diagrams is actually simple as long that we remember the one we had. So this is power supply unit. Then here we have combinational logic circuit, combinational logic circuit. This is input unit. And then here we have another block. Here we have output unit. Then here you have memory element. Then for this case you have a power supply. Here we have an input. Here we have an output. So you can have, as I said, you can have more than one input and you can have more than one output. So stop writing and stop drawing. Look here, the blackboard. Look here. So for the memory, this is the output. We take the feedback from the output, the memory element. Hello? Yes. Ha, 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 ha. Then we take the signal from here and feed our memory element. Then we can take feedback. Because we are mechanical guys, we know that in engineering we have some system with feedback and some system without feedback. Then this feedback or the information from the memory element will be also combining with the input. So this is previous state. So do you see? Stop writing. This is the input unit. I told you that it's actually the system which interfaces with the real world environment. And in most cases, it might be a mechanical and electronic system, mechatronic system. Because there's a mechanical structure and electronic structure. I said, stop drawing. Tell your neighbor, stop drawing. Look at the blackboard and listen. Okay. So this is the input unit. Suppose that this is the time when I want these circuits to operate. Remember, this is the power supply unit. It powers the input unit. it power the combination logic circuits, it power the output unit, but also this power supply power what? Power also the memory element, because the memory elements is electronic system, need power. It's just like you. If you want to remember something, you need some biological power, right? That's why that if you are hungry, you cannot work, you cannot think, you cannot remember. You can ask your neighbor, just give me some time. Then I will give you the feedback about what you have asked me. So whenever you find the file by that time, file is not found. File is not found. So at this time, this is the input units providing the signal into the combinational logic circuit. Then the combinational logic circuits combine these inputs at the present state and provide the output unit. And this output unit is going to actually affect mechanical systems or mechatronic system or electrical systems or computer system or biomedical equipment system. Okay? Are we together? So at the same time, when the combinational logic circuits provide the output signal to the output unit, then some wires also take small amount of these electric currents that will be fed into the output unit and fed into the memory elements. So the memory elements will be keeping the states of the previous states of the output. Listen. For instance, let's say that this input is 1. When it has been processed, then we get the output of 0. So these bits of 0 will be taken by this wire and be kept here. Hello, students. You are not paying attention. This is our last today's concept. Pay attention, listen, understand. I won't write a lot. Check your neighbor there, backbench. He's busy. Let me start. The main function of power supply is to provide power into different parts that needs power for them to work. Just like the main functions of the food that we are taking is just to give our body to function. Ability to function or energy to function. So you may decide to walk or you may decide to sleep. And the goodness that whether you walk or whether you sleep, you'll feel hungry again for the next time. The food has been consumed. That is God's creations or God's wonders. Whether you work or you don't work, the food will be consumed within the body. Right? Then, so if the input gets the power signal, it can sense the real world environment. Then provide the outputs to the combinational logic circuit. Suppose that the digital signal provides the combinational logic circuit is 1. Right? Which is 5 volts. Hello. Then, this signal is being processed by the combinational logic circuits, whether it is being multiplied with another signal, whether it is being inverted, whether it has been added, whether it has been actual that reversed or whatever. Then suppose our output bits or output digital signal is 0. Right? So when this output is 0 is being fed to the output unit, at the same time, this bit 0 will be taken to the memory elements and being kept. So if it will be kept, it means that for the next combination of the inputs, we have the previous state which is 0. Are we together? So after a few seconds, if you want to get the output, then what happens? These memory elements will bring the previous state of the output, which was 0, and being combined with 1, and get another new output, which might be, for instance, 1. This 1 also it is taken into the memory, right? For the next combinations, then this 1 will be fed in the inputs and be combined with the input to provide the output. That's how the process goes on. For that case, it means in case of the memory, we have something we call the set and the reset. Set and the reset. Set and the reset. In computer, we used to have restart and the shutdown. So restart is actually you are restoring the previous. It means that you are telling the computer to refer the See, that's why if you restart your computer, you lose all the previous work which you did not save. Are we together? Are we together, class? Yeah, so this is figure 2, the general block diagram of sequential logic circuit. So I've tried to use a simple language to teach you about this block, but actually there's a lot of information which have been hidden there. But that is the fundamental principle. And you are the mechanical guys, we have to teach you fundamental skills or fundamental stuff. Are we together? Yes. Yeah, so in memory there is set, reset, set, reset, set, reset. And what the memory actually keeps, it does not keep your music. The memory elements does not keep your names. The memory elements it just keeps the binary number or digital signal, whether 0 or 1, that's all. Are we together? Okay, do you have any question up to this part? No. Okay, so if there's no any question, I would like to tell you that this is the end of lecture 1. Join me in lecture 2, where I will teach you about combination logic circuits, and we'll be starting about the fundamental building block, that is logic gates. And we'll learn them, just we remind you some few concepts that you have learned in science, or in mechanical engineering, or maybe in engineering when you've been in ordinary diploma. And then once you have covered that concept, but we'll take you or will add some value about engineering knowledge of digital electronics. So this is the end. Make sure to invite your colleagues for the next lecture. That will be lecture 2, because we are going to discuss about some of the new concepts for the mechanical engineers. So this is the end. I would like to thank you. Let me ask you about you. Have you understood what you have learned? Yes. Yeah, so if you have understood, always myself have a tradition to appreciate students who have understood what I have taught them. So if that's the case, let me congratulate you and let yourself congratulate yourself. So let us congratulate ourselves. So let us prepare. Have a clap, because it's always people, they don't appreciate us, right? They always say that you don't do 1, 2, 3. Hongera. Imara. Wow. Very beautiful song. When you've been in kindergarten, we were thinking school, playing. School, playing. Not like nowadays you are thinking about rental charge, think about binary number in food. Thank you very much. See you.
Thank you, sir.
You're welcome.